Okay, so we remember the Klein-Gordon equation. Right, we derived this equation plus h bar squared, two derivatives, phi. I think we wrote psi, but we're writing phi because that's sort of normally what's used. This is equal to 0. This is it was a one-dimensional system, right? This would otherwise would be a del squared, and we ended up. We started from here. We ended up at the concept of a field of simple harmonic oscillators. And now we sort of want to, for consistency, to understand this formalism better, start from the perspective of a field and end up at the Klein-Gordon equation. So to do that, and maybe we can simplify things for ourselves by doing h bar equals c equals 1, then this equation becomes minus phi double dot plus that minus m squared phi equals 0. Okay, so we want to see how this equation can be obtained by considering a classical, i.e. a non-quantum field that we then turn into a quantum mechanical thing by imposing quantum commutation relations. That's where the quantum physics really comes in, right? That's the uncertainty principle. And this is the opposite, again, of what we did before, where we started with quantum operators and relativistic energy. This kind of thing, we ended up there, and then we showed that we end up at the simple harmonic oscillators are needed, and you end up with a field, a collection of simple harmonic oscillators. Now you can't just describe one particle. In other words, you end up at a field. Okay, so we want to sort of do the opposite. We want to start with a Lagrangian, and we want our Lagrangian, of course, obeys. It has to be compatible with special relativity. So we're going to write this. If you remember the lecture in the analytical mechanics course, we're going to generalize the Euler equations. So we have dl by d phi by dx mu. Right, mu goes from 0 to 3, so it's both space and time, or time and space, minus dl by d phi equals 0. So if we have a one-dimensional system, so there's only an x1 and x0 is really time, so this looks like d by dx0 of, so we're summing on mu, right? dl by d phi by dx0 plus d by dx1 dl by d phi by dx1 minus dl by d phi. That has to equal to 0. And so we can sort of, given this structure, we can sort of see what kind of L we need in order to end up here, right? We need two derivatives in time, two derivatives in space. In this case, it's only x because it's the del squared is just, this has it's a one-dimensional system, so it's just second derivative in x. So, right, we need two derivatives of phi in t for this term, and we need two derivatives of phi in x, and therefore, given that both of these two things are treated in the same way here, we're going to have, our L is going to be made up of phi dot squared, right? We notice the kinetic energy kind of structure here, right? This is the structure that goes into kinetic energy. If this were a position, this is the velocity squared. And so we also need a term that has d phi by the x squared. So these are the two terms. Let's put a semicolon here. We're not multiplying. We're going to add these two terms together. And then we also know that we need a phi to emerge from here, and that comes from this term. And so it's clear that the fact that we need a phi in the equation of motion, so to speak, that's what they're called, right? The Euler equations have to end up here. This is going to require a phi squared in the Lagrangian. Okay, so, and then we can also see what signs we need there, because we need a negative here, positive here, and a negative m squared there. So this, it's not too difficult to recognize that our Lagrangian has to look like phi dot squared over 2. Then we have the same over 2, but we have a minus sign here, so minus a half. The d phi by the x squared term, and then we have a minus sign here, and we have the m squared. We also have the 2 there, phi squared. That's the Lagrangian. And so let's just rewrite what this equation looks like. Let's replace x0 with t and x1 with just x. That looks like d by dt of dl by d phi dot, that will just derivative in time, plus d by dx d phi by d, oops, what did I do there? D by dx1, so that's d by dx of dl in with respect to d phi by dx minus dl by d phi. That has to equal to 0. And so this becomes, right, we see this is phi dot, that becomes phi double dot. We apply that. Then we have this, we have a minus sign here. So here we get a minus, similar kind of thing. We just won't indicate it with dots because it's with respect to space coordinates. And then the last term gives us the plus sign, or we just get the equation flipped inside. Plus m squared phi equals 0. So it's the same equation. It's the Klein-Gordon equation. And we can sort of see that this kind of thing is nothing more than a collection of objects of mass connected by springs. So these are a mass on a spring. So let's put a spring like this that can vibrate up and down, but also connected to another one here. We'll see where this comes from. So these can vibrate up and down. And this accounts for, let's make this one stretch out like that. And then we have this one, and then we have a spring here connected and so on. This one means it's been stretched like that. And so on. It's a collection of simple harmonic oscillators, but they're coupled. They're all connected to each other. These are all of mass m. Spring, you have a spring here. And so this is kinetic energy and potential energy for the spring going up and down. But this term here involves the coupling, this spring here, if you will. And so really we think of small oscillations here, and you'll get a term like this. We kind of want to massage this kind of thing. We want a continuous kind of object. So really we're thinking of taking the limit as this distance goes to 0. And there's a little bit of ambiguity here, because what does it mean for masses and springs when you're taking the limit to 0 and you want everywhere in space to be exactly the same? But basically we can get a sense of this by looking at this and seeing that we have this is the displacement there. We we have a triangle there where the distance, this is sort of the x direction, this is the x direction, and this is phi. So this is x, and this is phi, and this is therefore x squared plus phi squared square root. And we want the limit, we want to consider the limit for small displacements of x squared plus phi squared. We could call that y, x squared plus y squared, x squared plus phi squared, as phi or y goes to 0. And this becomes 1 plus phi squared over, I think it's 2x squared. When we don't displace it, right, then this is 0, and we don't have these things are all in their equilibrium positions. This doesn't add anything to the potential energy that turns into any physics, right? It'll cancel out in Lagrange equations. So this is the thing that really matters. And basically what we're arguing is that it's a phi squared term that is needed. And so we can kind of understand that this term here captures this, the potential energy of this stretched region in here as you displace this up and down. And we could think of having 2 and 3 dimensions, right? You have rows of these kinds of things in 2 and 3 dimensions, in and out. That's just a one-dimensional system. And so, of course, the solution to this are waves. We know this. And then on those waves, we impose the commutation relations, right? And that's the uncertainty principle, and we are at a quantum field theory for a free field.